Okay, this is going to be over section 5.3, contact forces and friction. The contact force between two objects can always be represented in terms of a normal component, N, perpendicular to the surface of interaction, and a friction component, F, that is parallel to the surface. So when sliding occurs, the kinetic friction force, F sub k, is often approximately proportional to the normal force. Then the proportionality constant is mu sub k, or the coefficient of kinetic friction. When there is no relative motion, the maximum possible friction force is approximately proportional to the normal force. And the proportionality constant is mu sub s, or the coefficient of static friction. The governing equation is friction static, the static friction force is going to be less than or equal to the coefficient of static friction times the normal force. The actual static friction force may be anything from 0 to the maximum value given by the equality in equation 5.2, and it does depend on the situation. So usually mu sub k is less than mu sub s for a given pair of surfaces. In other words, if you have friction here, which is going to keep the box motionless, and you start tugging on it, the friction is going to oppose that particular change in its acceleration. Obviously, the weight and the normal force are going to be directly opposed to each other, but you're going to have to tug on this box in order to be able to overcome the static friction force. And the static friction force is going to be equal to the tension force up to a certain point. Once that maximum friction force is applied, you can see that the friction falls off to something that's less than this force, and this is called the kinetic friction. Okay, so friction and normal forces are really components of a single contact force. So you've got the frictional component, which is going to resist any sort of push or pull in this direction. You've got a normal force component, which is the surface pushing back on the block, and you've got the weight. And so you've got a contact force. You've got what's pushing up this direction, you've got what's resisting motion in this direction. So the friction force and the normal force are always perpendicular. This equation is not a vector equation, but a relationship between the magnitude of the two forces. A frictionless surface means that this value becomes 0. The more slippery the surface, the smaller the value of the coefficient of friction. So for Teflon on steel, the coefficient of kinetic friction is about 0.04. For rubber tires on rough, dry concrete, or sneakers on a dry gym floor, it can be as large as 1.0, 1.2. For two smooth metal surfaces, it can be 0.4 to 0.8. So these are approximate values. They're kind of put together just sort of based on experiment and trying to correlate what is happening when one surface runs over the other. If you get down to the microscopic level here, you're going to notice that a smooth surface is not really smooth. It's rough. And so these surfaces catch and cling to each other, and that's what creates the friction. This is just another description of what I had gone over with in the summary, where if you've got no applied force, your friction force is 0 because it's not resisting anything. You start applying a weak force in this realm, the static friction force is going to be enough just to resist what's going on. You can see the tension force here and the frictional force on this axis. So in this particular region, the tension is going to match the friction force, and it's not going anywhere. Once it gets up to this particular point, you're going to see that the coefficient of kinetic friction is going to drop. And it looks even a little bit jagged as the tension force increases. However, it does remain fairly close to a constant level. And again, your static friction is going to be less than or equal to the coefficient of static friction times the normal force. And this, of course, has no units. It's just a coefficient that tries to correlate the normal force and the static friction force. So again, you've got some more examples down here. I would encourage you to go through those so you can get a better feel for what's going on. And we will move on to section 5.4.